Let's go through Liquid 1206 design skip list. So it defines a skip list is a data structure that take a log and time complexity to add, erase, and search. So it needs us to implement search, for example, whether in this data structure we have this target, or add a number, or erase a number. Erase, that means it will return true or false. That is, if if data exists in this data structure, or return true and remove it from our data structure. So let's look at what is a skip list. So this picture gives us a good hint what is a skip list. So so you will see at the lowest level, we insert every number. So, and the highest level, we are going to have possibly very few number on the highest level. And for every level, it is a linked list. And this linked list, the data are in our ordered sequence. So you'll see 30 will link to next to be 40, and 40 next to be 50, and blah blah, right? And on the level 2, we'll see 30. We don't have 40 and 45, right? So we only have 50, and 50 goes to next to 70, and go to now. And level 3, 30 goes to 50. And level 4, 30 goes to now. So we'll see every time we have the level increased by 1, actually the number of nodes was called each node, right? So it's going to have the possibility to be choose to be have half of the chance, right, of 50%. So we need to implement the search, add, and erase. So let's look at the search algorithm. Assume we are going to use a level instead from 1, right? We can define whether it's 1 to 1, 2, 3, 4. We can define this from level 0, okay? Because we are always going to insert everything to level 0. For example, we have 30, 40, 50, 60, 70, and we don't put the 80 here, and the 90, and it goes to 0, right? So this is at level 0. And before we add this level 0, normally for linked list, we would like to have a dummy head, right? Head was the -1 as dummy, and this is level 0, and pointing to 40, pointing to 50, pointing to 60, 70, 90, right? And the tail is unknown. And so for the search, let's say it is kind of straightforward, right? So when we search every node, we are going to define a node, and a node should have value, and also a next and a down, right? Let's see, just look at the picture. So it's going to have 2 pointer. Next, well, right? We can call right will be the greater in the same level, the next greater number node, right? Node with the next greater number. And down will be, if there is a down, right? The data will be, the number will be the same. So, um, let's look at how it is. So this is level 0, level 1, right? Level 1, we'll see we have 30. So if we have 30, and we are going to have a dummy as well, right? And we're going to have goes to 50, and it goes to 70, and 50 has done. 70 has done, right? And 70 goes to now. And then level 2, that is -1, we're going to have 30 has done, and 30 goes to 50, right? And it goes to now. And level 3, we use 0, 1, 2, 3, right? But you can also define as 1, 2, 3, 4, and -1, and there is still 30, and it goes to now directly, right? So how does this one search? So what is our search process? So let's look at search, right? So for example, we want to search if 60 exists in our data or not, in our data structure or not, right? So the steps what we're going is that it goes to the Harris level, right? So in this, right now it is 3, right? So we go to Harris level. We find from left to right, from the dummy to we just go through the use a right pointer to go through the nodes, right? So we'll see find this is 30. And after 30, whether we have anything greater smaller than 30, we'll find this after 30 is already none, right? So at this level, we don't we stopped at node 30. Then what we need is that we go down to the next level. And we're looking for 60, right? And at this level, we'll see initially we are at 30. Then we go to right, we find another number smaller than 60, that is 50, right? So we go to here. And after 50, we didn't, it's still none. We didn't find the 60, right? So from 50, we go down and go down to this node. Now, 50 at level 1, on its right is 70 already, right? So we cannot go to right anymore. So we from 50, we go down to level 0, and we go right? We find 60. So we return true. So this will be, we find this will be search path, right? And for add, for example, now if we want to add a number, right? For example, we add 80. So what should we do? So we should still have a search process. This search is a log and time complexity process. So we search first. So still the same, right? And 80 well goes to this one, right? Because 70, we have found out 70, and it go down. So the path is like this. And after 70, and we find 90, right? So we know where should we insert the new nodes. We should insert our new nodes here, right? But after you insert these two, um, we know we should insert a node here. And what we are going to do is that let's do this. Let's instead of I'm not going to use 80 because 80 this number. So for this one, we are going to we don't know its level, right? So we're trying to have a possibility, 50% of possibility it goes to level 1. So if it is at level 1, right, it will be here. And if we insert um, 80 at level 1, we still have another 50% multiplied by 50% to go to level 2, right? So if we calculate, we have a possibility function that it is going, we are going to insert 80 at level 2, right? So so what we do is that we are going to stop here. So the insert process, what we do is that we let's look at the insert process. We are put head at here, every data structure at here, which is the highest level the head, and then it goes to 30, goes to 30, go to 50, and now we know we're going to insert 80 at here, right? And we are going to still go through the previous pass 50, go down, and goes to 70, right? So 70 insert next to be 80, and go down 70, 70 insert next to 80. So this will be the process we are going to insert. Let's go through another example, for example, 45, right? So if 45, we calculate 45 should be here, right? But we calculate the possibility it will have let. So this one will be, for example, if we are going to stop at here, right? Level 1. And we have 50% go up, but now it's not going up. Then so the process we do is that we search find a position. Then what we do is that we go through the paths like this, right? And have this one connect to 45. But let's look at another case. The 45, because this just have chance, right? Have chance to be 45 to be level 2, and have a chance to be level 3. And if it happens that we have 45, have chance to calculate it, that we need to, it has a level greater than our data structure level, right? Then what we do is that we still we have another level here, right? Then what we need to do is that we have a dummy head, create a dummy head here, and also have this dummy pointing to 45. So in this case, what we have is that we are going to this path. Let's look at the path. So the path is this dummy, right? And go down still to dummy, and this dummy, and at level 3 there is 30 here, right? So we go to let's look at it. So it goes to 30, right? And then go to 30 and pointing to 45, and it should be like this. So this will be the add process, is that we are going to have dynamically have a chance to have the level go up. So doing like this, the space complexity will also be log n, right? Because we'll see this one has the level 0 will have 100% possibility every data are going to insert. And level 1 will be 50%. Level 2 will be 25%. And level 3 will be 1.12.5%. And so if it goes to, for example, 16, right, it will be very low possibility to be a high level like a 16. So one of the optimization is that we can set a max level, for example, max level to be 16, right? After 16, we're not going to increase the level anymore, right? We just stop at this 16, because the chance to go to level 16 will be very low, right? We can set the maximum level here. so that the space will be constant. So this will be the process of add. And for erase, right? Erase, that will be also similar. So we trying to search, for example, at here, right? The header. Uh, so let's remove some of the. So let's look at we are trying to insert is to delete, erase the data 45. Okay. So what we do is that we look at this one, right? We find the 45, right? So we still go through the same level, the data ahead of it, right? Just a smaller the one, right? Largest smaller one. So this one goes to 45, right? And then go to here. So have this one pointing to next. And then have 30 pointing to 50. And then have 30 pointing to 50 and have 40 pointing to 50, right? So still the path is like this, right? So the erase is the same process. So we just need to implement the whole logics, right? So to implement, we need to have a class node, and this node needs to have a value, and the node should have a right pointer and a down pointer, and I'm going to have a constructor into value node right node down. So I can have this dot value equals to value. This dot right equals to right. This dot down equals down, right? And so for the whole data structure, we're going to have a, a head, right? So the head will be the highest level head, right? Dummy. So we'll create a dummy here. So what we need is that a private node head, and we are going to have a private int level will be current level, right, for the whole data structure. And we are going to use a private random, right? We use this one to have to get the 50% um whether for the level plus one we are going to insert or not. And we can also have a private static final. For example, we are going to have a int. Um, let's have a static final int max level to be 16, right? This one is optional, right? If you want to keep the space to be log in, um, you don't need this line, right? But uh, just to avoid extreme cases, for example, we may have this will be very long. It's possible, right? We have very small chances. For example, we have 30, 32, right? Long tail in one of the nodes, but it goes to 32, and then the next level, next data goes to, for example, 10, level 10, right? So this is apparently not then we still need to do search each level, not efficient, right? So we can have max level here, but we'll see. Level 16, it is 2 to the power minus 16 chance to get that. So the chance is, the possibility is very low, but we can set max level here. So for the constructor, we're going to have head equals new node -1 now and now. And we're going to have a level, means this data current, this data structure current level is 0, right? Random equals new random. And for search, right, we just have a dummy node current equals head. And we'll say why this current doesn't equal to null. So first is that for this kind of at a level, this head is the Harris level one, right? So from the Harris level, we're going to check it's right. So we'll say y current dot right down equal to null, and current dot right dot value smaller than target. Then we're going to have a current equals current not right. So the current is going to always at this level, the greatest smaller than target. Greatest smaller equal to, right? So we need to have a check if current dot right equal to null and current dot right dot value equals target. We just need to return true, right? And for this level, if we didn't go to if statement, then we go to the level -1, go to the lower level. So we're going to have current down, right? So if we jumping out of this while we didn't find target, we just return false. So this will be the search process. So for add, right? Add. So we're going to use current level equals to 0. And we'll say while current level is smaller than max level. And we'll say and current level is smaller equal to the data structures level, right? And we'll see and random next int 2 equals, you can say 1 or 0, right? That is the 50%. Then we're going to have current level increase by 1, right? So we'll say if current level is greater than the whole data structures level, right? Then what we do is that we're going to have data structures level should equal current level or whatever. We can also write this one increase by 1. And we're going to have a head equals new um, um, new node, right? New node -1 now. And the down is head, right? So in this case, we pointing this one to we for our dummy, we also increase. So for add, right? Now we want to add. We want to search for the Harris level. We get the Harris level, that is current level, right? So current level, for example, we have 80, right? So you'll see if so what we do is that we search 30 whether there is 80, right? Search and to here 70 we find is next is 80. So we still going like the search process. Then from this 70 we go down for each and probably go right, right? Find the greatest smallest, then 80 for everyone. We insert 80 after the previous node. So what we do is we still need a node current equals head, right? So um, we are going to have for int level equals level and level greater equal to 0, level minus minus, right? So we'll see while this current dot right down equal to none and current dot right dot value is smaller than none, right? Then we're going to have current equals current dot right. So we'll find that each level the greatest smaller than number. So we'll say if this level is smaller equal to current level, right? So that is for this number, what is highest level? Um, then we'll have current dot right. We need to insert one node, right? Equals new node num current dot right, right? And we set it down to be none right now. And we'll have a current dot equals current dot down, right? And we also need to pointing to connect the down pointer, right? We can use a last variable here. Last initially set as none. Last will be for the high, level plus one, right? L plus one. If we insert one. So what we do is that if last does equal to none, we're going to have last dot down equals current dot right. And we also set the last equals current dot down, right? Current dot right, sorry, for this level. So this will be the add process. And for erase process, uh, implementation is similar, right? So what we do is that instead of we add a node, but we have a current. This current is always the smaller, the greatest smaller, right? Pointing to the node we are going to delete that pointing to its next right, right? So we are going to have a node current equals head, and we're going to have Boolean result equals to false, right? And for int level equals level L, right? Which equals to 0, L minus minus. Then what are we going to still? We are going to have while current dot right down equal to null, and current dot right dot value is smaller than null. Then we're going to have current equals current dot right. And if we are say if current dot right down equal to null, and we find this data, right? Current dot right dot value equals null. So we'll see we are able to delete. The result will be true. And what we do is that for this label, current dot right equals current dot right dot right. And then we move to the next level, move down, right? Return result. So this will be the code implementations for Skiplist. The Python code is similar. Let's also write the Python code, right? We need to define a class. Let's import random, and also we define a class node. And for this class, we need to have IT self value right equals none, down equals none. And we're going to have self dot value equals value, self dot right equals right, self dot down equals down, right? So initially, we're going to have self dot head equals node minus one, right? Self dot level equals zero, and self dot random equals random dot random, right? And we're going to have a self dot max level, for example, equals 16, right? And for search, we're going to have current equals self dot head. So what we do is that while current is not null, and while current dot right is not null, right? And the current dot right dot value is smaller than target. We are going to have current equals current dot right. And let's say if current dot right is not null and the current dot right equals target, then we return true. Um, Otherwise, we move down current equals current dot down. And if we moving out of this kind of while loop, return false. For add, right? Add. This is actually what's the current level? It's actually this node's level, right? We call, and what's it? This node's highest level. So we need to calculate. So we use a possibility while current level is smaller than max level, and current level is smaller equal to we should have self dot level and self dot rand int 0, 1 equals to 0, right? Then we're going to have a current level which should increase by 1, right? Plus equal to 1. So we have 50% chance. We need to have a level greater increased. So we'll say if current level is greater than self dot level, right? Then we're going to have self dot level equals the current level. So this is actually this node's highest level, and self dot head, we should put because this will be the highest dummy. And in this case, because we want increase one level, right? So we also need to have a new dummy self dot head, right? And when we we just have a cursor equals self dot head, and last equals none, right? This last will be level plus one, um, the the node we add. Okay, so we'll say for level in range, for L in range, self dot level minus one, right? And then we're going to have while current dot right, and the current dot right is the value is smaller than none. Then we're going to have current equals current dot right. And let's say if level is smaller equal to this number highest level, right? Then we're going to insert. for each level. Then we'll have current dot right. This current is always sitting on the previous or greatest smallest node in the same level, right? Equals node none current dot right. No. And we use the last, right? It's the previous node we insert. If last equal done equals none, we're going to have last dot none done equals current dot right. And and also we are going to have last equals current dot right. And then we move down, right? Current equals current dot down. So this will be add process. And for erase, so we are going to have current equals self dot head result equals false, right? So it is like a search because if it doesn't exist, then we don't need to erase. For L in range self dot level -1, right? We are going to have while current dot right is null and current dot right dot value is smaller than null number. Then we're going to have current equals current dot right. And if we find, right, if current dot right is not null and current dot right dot value equals number, then we're going to result equals true, right? That means we're going to have dot current right equals current dot right. Just have the previous pointing to next. And also we need to move down for current equals current down, right? So for every layer from here, we're going to to connect previous to next and return result. So this will be the code to implement. Node class, node. Name node is not defined. Do you know down is none, right? Let's look at this code. Random self node -1 0 random dot random max level. So current self dot head current right and current smaller than target. Then current equals current right if and equals between two, current equals current down. And for add, what we're going to do is that we have this one and smaller equal to, and this one equals to 0, then this one increase by 1. If this numbers is greater than self dot level equals current level, and then current equals self dot head last equals no for level equals while current dot right and current right the smaller the number because if this one smaller equal to current level, right? So we are going to current right equals number current right if last dot last equals current right, current equals current down, and erase result equals to false label if current right and current right current the value equals number result equal true, current equals down. So which one is not correct? Search, erase, which um what's the problem here? Random initial says no. Didn't find any problem here. Hmm. If between two to false and to increase by one. If greater than then we add self but we add a help and current self head as equal to none and so on and so on. Mm, while this one's small equal to currently current right equals node none current right no if last line equals no current last equal to current right current plus current down erase erase delta head while current right and current right smaller than now equals current right. If equals to now current we find that this result equal to true. So what's the problem here? Hmm. Let's comment this one first. But I don't think this is a problem, right? So we get this one simpler first. Still, this is false, so this is not a problem. Um, search. So search. Search current self head and smaller than target current equals if current right and current right equals target. Should be value. Okay. We compare that is compared to value, right? So this will be the Python implementations. The things that from here actually I'm not going to implement it anymore, right? But the things that we can implement Redis Z set from here. So Redis Z set is actually skip list plus a hash map. So for for the for the Z set, what we need is we need, for example, have a string called name, right? And also we have double, right? Double value, right? So what we do is that we introduce map to check if this data already insert in our skip list or not. So I'm going to just bring out the implementations here. Not this one. So about the Z set, right? How to implement Z set. So we are going to have a name for this member, also a scope. So and in our solution, we add a map, right? So here we use a possibility because we can also write the same way, right? But we um, just write like this, extract this as a function, right? And add is the same logic, and erase is also the same logic. And contents, we just need to check the map whether we have this data or not, and we can implement. For example, this score is get this is members score and the range, right? So range, what we need is that we should have a mean score and a maximal score, right? So this is also like a search, um, and also rank, and rank by rank. Uh, so the rank is also search, right? Search this data, what is the number, um, the top rank from the data structure, right? So it is like a search, but we have counts. So just I write this sample, but it will implement have more implementations. So that means that we know this set is just one more step of skip list. We add a hash map to our data structure, right? And use a skip list and a hash map. So this will be our implementation of a design skip list, the search, add, and erase are all log in time complexity.